Hello, and welcome to the Sleep Lab, where we explore the universe's greatest mysteries while you drift into peaceful rest. I'm so glad you found your way here tonight. Maybe you're nestled under soft blankets, the room dimmed and quiet, ready to let your mind wander among the stars. Tonight, we're embarking on a gentle journey to one of humanity's most profound questions. Is alien life hiding right here in our own solar system? Before we begin this cosmic exploration, if you find these soothing science adventures helpful for sleep, a gentle like really helps this channel reach other restful learners. And if you'd like to support more dreamy discoveries, consider subscribing or joining our Sleep Lab family with a super thanks. Your support keeps these peaceful journeys flowing through the night. Now, let's drift together into the quiet corners of our cosmic neighborhood and discover what alien life might be whispering in the darkness of space. Chapter 1: The Quiet Harbor of Home. You lie still now, breathing softly as the night wraps around you like a gentle embrace. Your body rests in the comfort of familiar surroundings. But tonight we invite your mind to drift outward, not into the vast unknown of distant galaxies, but into the surprising intimacy of our own cosmic neighborhood. The solar system, our quiet harbor among the stars, may not be the lonely place we once imagined. As you settle deeper into stillness, consider this: alien life might be closer than the nearest star, hiding in the shadows of worlds we've known since childhood, waiting patiently in places where no human eye has ever looked directly. For so long, when we dreamed of meeting alien life, we pictured dramatic encounters with beings from distant stars, their ships crossing the impossible void between solar systems to reach us. But the universe, as you'll discover tonight, often keeps its most profound secrets much closer to home. The search for extraterrestrial life has taken an unexpected turn in recent decades, one that leads not outward to the stars, but inward to our own celestial family. Mars, Europa, Enceladus, Titan. These are not just distant worlds in textbooks, but potential harbors for life, places where the story of biology might be unfolding right now, perhaps has been unfolding for billions of years, in forms both familiar and unimaginably strange. You don't need to travel faster than light to find aliens. You don't need to decode radio signals from distant civilizations or spot the glint of massive spacecraft against the star field. The most revolutionary discovery in human history might come from a robot rover sampling Martian soil, or a probe diving through the icy geysers of a small moon orbiting Saturn. As you breathe in the quiet darkness of your room, spacecraft are already there, already searching, their instruments designed not to hear alien voices, but to detect something far more subtle: the quiet chemical whispers that life leaves behind wherever it takes hold. This is not the science fiction of invasion fleets or cosmic federations. This is something gentler and perhaps more profound: the possibility that life is not rare, not precious in its singularity, but abundant, adaptive, persistent. The kind of life we might find in our solar system won't build cities or send messages. It will be microbial, perhaps no more complex than the bacteria that thrive in Earth's deepest caves or hottest springs. But in its quiet existence, such life would answer one of the most fundamental questions we can ask: are we alone? And the answer, whispered in the chemistry of alien cells, might be a resounding no. The search unfolds with the patience of deep time. No sudden revelations, no dramatic announcements that change everything overnight. Instead, scientists follow threads of evidence as delicate as spider silk. Unusual chemical signatures in the Martian atmosphere that pulse with the seasons. Organic molecules discovered in ancient lake beds on Mars. The complex chemistry detected in the plumes of water vapor shooting from beneath the ice of distant moons. Each discovery is a breadcrumb on a trail that might lead to the most important realization in human history: that life is not unique to Earth, that biology is not a cosmic accident, but a natural consequence of chemistry and time. As you drift in the comfort of your bed, consider how this changes everything. Not just science, but philosophy, religion, our sense of place in the universe. If microbial life exists on Mars, it might share a common ancestor with life on Earth. Blown between planets on meteorites during the violent early epochs of solar system history. Or it might have arisen independently, proving that life is not a miraculous fluke, but a natural outcome wherever the right conditions persist. Either discovery would be revolutionary. Either would mean that life is far more common than we dared hope, that the universe might be teeming with biology, from simple microbes to complex ecosystems we can barely imagine. The tools we use to search are marvels of gentle precision. Spectrometers that can taste the chemical composition of a planet's breath. Microscopes that can peer into samples smaller than grains of sand, looking for the telltale structures that only living things create. Drilling systems that can pierce through ice and rock to sample the hidden waters below. These instruments are our ambassadors to alien worlds, extensions of our curiosity, designed to detect life not through grand gestures, but through the subtle signatures that biology cannot help but leave. Isotope ratios that hint at metabolism, organic molecules arranged in patterns too complex for non-living chemistry, seasonal changes in atmospheric gases that suggest active biological processes. Even the definition of life becomes more fluid as we search. We're not just looking for DNA and proteins, the specific chemistry of Earth's biology. We're learning to recognize life by its patterns, the way it stores and processes information, the way it builds complex structures from simple building blocks, the way it leaves chemical fingerprints that speak of energy flowing through organized systems. Life might use different chemistry on different worlds: methane instead of water, silicon instead of carbon, but it will still follow the same deep principles that govern all living systems: growth, reproduction, metabolism, adaptation. The implications stretch far beyond biology. If we find life in our solar system, it suggests that life might be everywhere in the universe, arising wherever conditions allow, adapting to environments we never thought could support biology. Frozen moons with subsurface oceans, planets with crushing atmospheres, worlds bathed in radiation. All of these might harbor life adapted to their specific conditions. The universe might not just be vast and beautiful, but alive, filled with an abundance of biological creativity that makes every star system a potential laboratory for evolution. You rest now in a universe that might be far less lonely than we imagined. Somewhere above you, Mars turns slowly in its orbit, its rusty surface hiding ancient riverbeds and perhaps ancient life. Jupiter's moon, Europa, orbits in the distance, its global ocean stirred by tidal forces, warmed by gravitational friction, possibly teeming with alien microbes that have never known sunlight. Saturn's moon Enceladus breathes water vapor into space through cracks in its icy shell. And in those plumes, complex organic molecules dance in the cosmic cold, carrying the chemical signatures that might spell out the presence of alien biology. This is where we begin our journey tonight, not with speculation or fantasy, but with the real, gentle, persistent search already underway. The question is not whether alien life exists in our solar system, but where we'll find it first, what form it will take, and how its discovery will change our understanding of life, death, and our place in the vast, patient, possibly living universe that cradles us all. Chapter 2: The Ancient Whispers of Mars. Mars drifts silently through the darkness, a rust-colored world that has captured human imagination for centuries. You float in your mind above its dusty surface, feeling the thin whisper of atmosphere, sensing the profound quiet of a planet that once sang with the music of flowing water. This ancient world, forth from our sun, holds secrets written in stone and soil, memories preserved in mineral deposits and carved into canyon walls. Tonight, as you rest in the gentle embrace of your bed, we explore these whispers from Mars's distant past. When rivers carved valleys, lakes filled ancient craters, and life may have first stirred in waters that have long since vanished into the cosmic void. The Mars we see today is a desert world, its surface scoured by endless winds, its sky a pale butterscotch that fades to deeper amber at sunset. But this apparent desolation is deceiving, for Mars carries within its rocks and regolith the fossilized memory of a radically different world. Billions of years ago, this planet was not the frozen wasteland we observe today, but a place where liquid water flowed freely across its surface, pooling in vast lakes, rushing through river channels, and perhaps even forming an ocean that covered nearly a third of the northern hemisphere. The evidence lies everywhere, written in a language of stone that scientists are only now learning to read with the patience and precision that such ancient stories deserve. NASA's rovers have become our gentle ambassadors to this distant world, rolling slowly across Martian terrain with the measured pace of careful explorers. The Curiosity rover, which has wandered the floor of Gale Crater since 2012, recently discovered something remarkable in the foothills of Mount Sharp. Wave ripples preserved in ancient stone, the kind of delicate ridges that form only when wind-driven water laps against shallow shores. These tiny undulations in rock, no larger than the ripples you might create by trailing your finger across a calm pond, represent some of the strongest evidence yet that liquid water once lay open to the Martian sky, unprotected by ice, stirred by ancient breezes that carried the chemistry of a living world. The discovery astonished scientists because it came from what they call the sulfate-bearing unit, a region they expected would reveal only evidence of Mars's drying phase, when the planet was transitioning from its watery youth to its current arid state. Instead, Curiosity found what mission scientists describe as the clearest evidence yet of ancient water and wave activity encountered throughout the entire mission. These wave ripples could only have formed under specific conditions: liquid water open to the atmosphere, shallow enough for wind to create surface waves, persistent enough for those waves to leave their mark in sediment that would eventually harden into stone. It's as if Mars preserved a moment from its aquatic past, a easy snapshot of wind and water dancing together under an alien sky. But the ripples are just one thread in a vast tapestry of evidence that speaks to Mars's watery history. The planet's surface is crisscrossed with networks of ancient river valleys, their branching patterns eerily similar to the tributaries that feed Earth's great rivers. These channels carved their way through Martian bedrock with the persistence of flowing water, carrying sediment from highland regions to lowland basins where it accumulated in layered deposits that tell stories of seasonal floods, persistent streams, and gradual climate change. The sheer scale of these water features is breathtaking. Some of the outflow channels are larger than the Amazon River, carved by catastrophic floods that released volumes of water almost impossible to comprehend. Deep beneath Mars's current surface, in regions where no human eye will likely ever look directly, recent seismic studies have revealed an even more intriguing secret. The Mars InSight lander, during its 4-year mission to listen to the planet's geological heartbeat, detected evidence of vast reservoirs of liquid water still existing today, trapped within the rocky crust some 6 to 12 miles below the surface. This hidden Martian ocean may contain enough water to create a global surface layer over half a mile deep, locked away in porous rock formations where it has persisted for potentially billions of years, protected from the harsh radiation and thin atmosphere that would quickly boil away any surface water in the current Martian environment. The implications of this subsurface water are profound and humbling. If life ever took hold in Mars's ancient lakes and rivers, it might have retreated underground as the planet's climate changed, adapting to conditions in these deep aquifers where liquid water still flows in eternal darkness. Microorganisms on Earth thrive in similar environments, in deep groundwater systems, where they derive energy not from sunlight, but from chemical reactions between water and rock. These subsurface biospheres can persist for millions of years in conditions that would seem utterly hostile to surface life, suggesting that Mars's hidden waters might harbor living ecosystems right now, as you rest quietly in your bed, evolving and adapting in caverns and fractures far below the planet's wind-swept surface. The story becomes even more compelling when we consider the chemistry preserved in Martian rocks. The Perseverance rover, currently exploring Jezero crater, has identified organic molecules, carbon-based compounds that on Earth are associated with biological processes. These aren't necessarily signs of life, as organic molecules can form through non-biological processes, but their presence in rocks that formed in ancient lake environments adds another layer to the growing body of evidence that Mars once provided, and might still provide, the chemical conditions necessary for life to emerge and persist. Perhaps most intriguingly, Mars continues to surprise us with signs of seasonal activity that hint at ongoing biological processes. The planet's atmosphere contains methane, a gas that on Earth is predominantly produced by living organisms, though it can also arise from geological processes. What makes Martian methane particularly interesting is that it appears to vary with the seasons, increasing during the warmer summer months and declining in winter. This cyclical pattern is difficult to explain through purely geological processes and has led some scientists to speculate that it might indicate seasonal biological activity. Perhaps microorganisms becoming more active when temperatures rise, then retreating into dormancy during the harsh Martian winter. The timeline of Mars's transformation from a potentially habitable world to its current state unfolds over billions of years, a gradual transition that began around 3.8 billion years ago, when the planet started losing its magnetic field. Without this protective shield, solar wind began stripping away Mars's atmosphere, reducing atmospheric pressure until liquid water could no longer exist stably on the surface. But this process took millions of centuries to complete, meaning that any life that emerged during Mars's habitable period would have had ample time to adapt to changing conditions, perhaps developing survival strategies that allowed it to persist in subsurface environments even as the surface became increasingly hostile. The possibility that life originated independently on Mars carries profound implications for our understanding of biology throughout the universe. If life arose twice in a single solar system, it suggests that the emergence of biology is not a miraculous accident, but a natural consequence of chemistry and time wherever suitable conditions persist. Alternatively, if Martian life shares a common origin with Earth life, perhaps transferred between planets via meteorites ejected during asteroid impacts, it would demonstrate that life can survive the incredible journey through space and seed new worlds, a process called panspermia that could distribute biology throughout entire solar systems. As you drift toward sleep, your breath slowing to match the rhythm of Mars's own patient rotation, consider that somewhere above you in the night sky, this ancient world continues its slow dance around the sun, carrying within its rocks and hidden waters the potential answers to humanity's deepest questions about our place in the cosmos. The rovers continue their methodical exploration, their instruments designed to detect the faintest chemical whispers that might spell out the presence of alien biology. Each sample they analyze, each photograph they transmit, each measurement they record adds another piece to the puzzle of whether we are alone or whether life, in its infinite creativity and persistence, found a way to flourish on multiple worlds within our own cosmic neighborhood. Mars calls to us across the void not with radio signals or visible cities, but with the subtler language of chemistry and geology, written in the stones beneath ancient lake beds and flowing still in hidden aquifers that know no sunlight. The red planet's whispers speak of water, of chemistry, of time deep enough for evolution to work its patient magic, and perhaps, if we listen carefully enough, of life itself. Chapter 3: Europa's Hidden Ocean. Symphony. Beneath a shell of ice thicker than mountains, Europa holds a secret ocean larger than all of Earth's seas combined. You drift now, in the quiet of your room, but let your mind float outward to this extraordinary moon of Jupiter, where beneath an alien sky, water moves in darkness that has never known sunlight. This is not the frozen wasteland you might imagine when you think of the outer solar system, but a dynamic world where tidal forces create a symphony of motion, where ice cracks and reforms in patterns that speak of liquid seas stirring far below, and where the chemistry of life might be unfolding in an ocean that has remained liquid for billions of years. Europa appears deceptively simple from a distance, a smooth ivory sphere marked by delicate brown lines that trace across its surface like brushstrokes on canvas. But this apparent simplicity masks one of the most geologically active and potentially habitable environments in our solar system. The Moon orbits Jupiter every 3.5 Earth days, locked in a gravitational dance with its giant parent planet and its fellow moons Io and Ganymede. This orbital choreography creates tidal forces so powerful they literally squeeze and stretch Europa's interior, generating enough heat through friction to maintain a vast ocean beneath ice that would otherwise be frozen solid in the frigid depths of space, where temperatures plunge to negative 370 degrees Fahrenheit. The evidence for Europa's hidden ocean comes not from direct observation. No spacecraft has ever drilled through that ice to taste the waters below, but from the subtle clues that magnetism reveals. When the Galileo spacecraft swooped past Europa in the 1990s, its instruments detected something remarkable. The Moon generates its own magnetic field, one that varies in strength and direction as Europa orbits through Jupiter's powerful magnetosphere. This can only happen If Europa contains a layer of electrically conductive material, and in the cold depths of space, that conductor can only be salt water. The magnetic signature tells us that somewhere between 15 and 25 kilometers beneath Europa's surface lies an ocean that may contain 2 to 3 times more water than all of Earth's oceans combined. This hidden sea exists in a realm of perpetual darkness, yet it may be far from lifeless. The tidal heating that keeps Europa's ocean liquid does more than simply prevent freezing. It drives a complex system of internal circulation that could transport nutrients, chemicals, and energy throughout the subsurface environment. The rocky seafloor beneath Europa's ocean experiences the same tidal stresses that flex the moon's ice shell, potentially creating hydrothermal vents similar to those that teem with life in Earth's deepest ocean trenches. These underwater hot springs could provide the chemical energy that life needs to thrive, creating oases of warmth and chemical activity in the cold depths of an alien sea. The James Webb Space Telescope has recently revealed something even more intriguing about Europa's surface chemistry. In certain regions where the ice appears to have been recently disrupted, areas scientists call chaos terrain for their jumbled, fragmented appearance, spectroscopic analysis has detected crystalline ice mixed with compounds that tell a remarkable story. Sodium chloride, ordinary table salt, appears on Europa's surface in concentrations that suggest it has been transported upward from the ocean below. Carbon dioxide and hydrogen peroxide have also been detected, chemicals that on Earth are often associated with biological processes, though they can form through non-biological reactions as well. These surface chemicals may be the fingerprints of Europa's hidden ocean, brought to the surface through a process that scientists are still working to understand. The leading theory suggests that Europa's ice shell is not a static barrier, but a dynamic system where material constantly cycles between the surface and the ocean below. Warm, salty water may rise through cracks and fractures in the ice, reaching the surface where it quickly freezes in the vacuum of space, leaving behind concentrated deposits of salt and other ocean compounds. Meanwhile, surface material enriched with oxidizing compounds produced by Jupiter's radiation may sink back down through the ice, potentially carrying oxygen and other chemicals that could support biological processes in the ocean below. The Hubble Space Telescope has provided perhaps the most tantalizing glimpse of this ocean surface exchange through its detection of water vapor plumes erupting from Europa's surface. These towering fountains of water shoot hundreds of kilometers into space through cracks in the ice near Europa's south pole, creating ephemeral geysers that appear and disappear with the moon's orbital position around Jupiter. The plumes are strongest when Europa is farthest from Jupiter in its slightly elliptical orbit, suggesting that the changing tidal stresses open and close pathways between the ocean and the surface. If these plumes carry material directly from Europa's subsurface ocean, they offer a potential window into that hidden world, allowing us to study ocean chemistry without the need to drill through kilometers of ice. Recent analysis of old Galileo data has provided additional confirmation of these plumes, as scientists discovered that the spacecraft likely flew directly through one of these water vapor eruptions during a close flyby in 1997. The subtle changes in Galileo's magnetic field and particle detector readings make sense when interpreted as the signature of a spacecraft passing through a column of ionized water vapor, evidence that these plumes have been active for decades and may represent a persistent feature of Europa's dynamic ice shell. The implications of Europa's ocean extend far beyond simple water chemistry. If life exists in this hidden sea, it would represent a form of biology completely independent of solar energy, thriving instead on the chemical energy provided by interactions between water and rock at the ocean floor. This chemosynthetic ecosystem would be similar to the communities of bacteria, archaea, and even complex organisms that flourish around hydrothermal vents in Earth's deepest ocean trenches, where sunlight has never penetrated but where life builds complex food webs based on the energy released by underwater volcanic activity. The potential for such life has captured the imagination of astrobiologists because it suggests that habitability may be far more common in the universe than previously thought. While surface habitability requires a delicate balance of distance from a star, atmospheric composition, and planetary mass, subsurface ocean worlds like Europa could exist throughout the outer solar system and beyond, heated by tidal forces rather than stellar radiation. These hidden biospheres could persist for billions of years, evolving complex ecosystems in the eternal darkness beneath ice shells that protect them from the radiation and temperature extremes of space. As you rest in the gentle darkness of your room, consider the remarkable irony that one of the most promising places to search for life in our solar system exists in perpetual night, beneath ice thicker than Earth's mountains, in an ocean that has never seen a star. The life that might exist in Europa's depths would know nothing of seasons, weather, or the warming touch of sunlight. Yet it could represent one of the most successful biospheres in the solar system, thriving in conditions that would seem utterly alien to surface-dwelling life like ourselves. The Europa Clipper mission, launched in October 2024, will arrive at Jupiter in 2030 to begin the most detailed study of Europa ever undertaken. This spacecraft will not land on the Moon's surface or attempt to drill through its ice, but it will map Europa's ocean from orbit, measure the thickness of its ice shell, analyze the chemistry of its plumes, and search for signs of biological activity in the water vapor that may carry samples of the ocean directly to space. The mission represents humanity's best opportunity to determine whether we are alone in our solar system or whether life, in its infinite creativity and persistence, has found a way to flourish in the hidden seas that lie beneath the ice of Jupiter's most enigmatic moon. In the quiet darkness of Europa's ocean, where no sun shines and no wind blows, life may be composing its own symphony, one written not in light and air, but in chemistry and warmth, pressure and flow. Tonight, as you drift toward sleep, that alien ocean continues its ancient circulation, its waters warmed by the gravitational embrace of Jupiter, its chemistry enriched by the slow dissolution of rock, its hidden depths perhaps teeming with forms of life that evolution has crafted for a world unlike any other. Chapter 4. Enceladus and the Breath of Life. Saturn's small moon. Enceladus breathes. Through fractures in its south pole, it exhales plumes of water vapor mixed with organic compounds, salts, and the very building blocks of life itself. You float now, in your imagination, beside this remarkable world, no larger than the length of England, yet harboring one of the most extraordinary discoveries in the history of planetary science. This tiny, ice-wrapped moon pulses with geological activity that speaks not of a dead rock tumbling through space, but of a dynamic world where liquid water flows in hidden depths, where chemistry unfolds in patterns that mirror the processes of life, and where the breath of an alien ocean reaches directly into space, carrying with it the potential answers to our deepest questions about biology beyond Earth. Before NASA's Cassini spacecraft arrived at Saturn in 2004, Enceladus was considered little more than a curiosity, the brightest object in the solar system, reflecting nearly 100% of the sunlight that strikes its surface, but seemingly too small and too distant from the sun to harbor anything more interesting than frozen water and ancient impact craters. The moon's diameter spans just 314 miles, making it roughly the size of Arizona, with a gravitational pull so weak that an astronaut could easily leap from its surface into space with a running jump. Yet appearances, as Cassini would soon reveal, can be profoundly deceiving in the outer solar system. The first hint that Enceladus might be hiding secrets came from magnetometer readings as Cassini flew through Saturn's magnetosphere. Something near the small moon was deflecting Saturn's magnetic field, creating disturbances that suggested the presence of an atmosphere or some form of particle emission. When the spacecraft finally turned its cameras toward Enceladus's south pole, the images revealed one of the most stunning discoveries in planetary exploration. Enormous geysers of water vapor and ice particles erupting from parallel fractures in the moon's surface, shooting hundreds of miles into space at speeds approaching 1,400 miles per hour. These fractures, which scientists informally dubbed tiger stripes for their distinctive appearance, stretch for over 80 miles across Enceladus's south polar region. The stripes are warmer than the surrounding terrain, still brutally cold by Earth standards at negative 135 degrees Fahrenheit, but warm enough in the context of the outer solar system to indicate active geological processes generating heat from within. The plumes emerge from specific points along these fractures, creating a complex pattern of jets and fountains that varies with Enceladus's position in its orbit around Saturn, suggesting that tidal forces are opening and closing the pathways that connect the surface to the hidden ocean below. When Cassini flew directly through these plumes in 2005, its instruments tasted the chemistry of an alien ocean for the first time in human history. The mass spectrometer detected water vapor as expected, but also a surprising cocktail of other compounds that told a remarkable story about the world hidden beneath Enceladus's ice. Carbon dioxide, carbon monoxide, nitrogen, methane, and acetylene were all present in the plumes, along with simple organic compounds like formaldehyde and hydrogen cyanide. Most intriguingly, the density of organic materials in the plumes was nearly 20 times higher than scientists had predicted, suggesting that complex chemistry was actively occurring in the subsurface ocean. The discovery of salt in the plume particles provided some of the strongest evidence yet for a liquid water ocean. When Cassini's dust analyzer examined individual ice grains escaping from Enceladus, it found that some contained significant concentrations of sodium chloride, ordinary table salt. This salt could only come from liquid water that had dissolved minerals from rocky surfaces, then been transported to the surface where it froze into the ice particles that Cassini observed. The saltiest particles were the heaviest, falling back to Enceladus's surface, while lighter, fresher ice crystals escaped entirely to form Saturn's Gossamer E ring, explaining why this ring appears to be made of relatively pure water ice despite originating from an ocean that clearly contains dissolved salts and other compounds. Perhaps the most remarkable discovery came in 2023, when analysis of archived Cassini data revealed the presence of phosphates in the plume particles, the first detection of this crucial biological element in any ocean beyond Earth. Phosphorus is essential for all known life, forming the backbone of DNA and RNA, powering cellular metabolism through molecules like ATP, and serving as a structural component in cell membranes. On Earth, phosphorus is often the limiting nutrient in biological systems, the element whose scarcity constrains the growth and complexity of life. Yet in Enceladus's ocean, phosphate concentrations appear to be hundreds of times higher than those found in Earth's oceans, suggesting an environment that could potentially support biological activity far more robust than anything we see in terrestrial marine ecosystems. This abundance of phosphorus points to active hydrothermal processes occurring on Enceladus's rocky seafloor, where tidal heating creates temperatures and pressures sufficient to drive complex water-rock interactions. The phosphates detected in the plumes likely originate from the dissolution of phosphorus-bearing minerals in the Moon's silicate core, a process that requires ongoing geological activity and liquid water in direct contact with rock. On Earth, similar hydrothermal environments at the bottom of the ocean support thriving ecosystems based on chemosynthesis, biological processes that derive energy from chemical reactions rather than sunlight. The implications extend far beyond simple chemistry. Computer models of Enceladus's interior suggest that the subsurface ocean may be global, encompassing the entire Moon beneath an ice shell that varies in thickness from about 12 miles at the South Pole to perhaps 35 miles in other regions. This hidden sea contains roughly 10 times more water than Lake Superior, maintained in liquid form by the heat generated as Saturn's gravity continuously kneads Enceladus's interior like cosmic dough. The ocean's depth may exceed 20 miles in some areas, creating a three-dimensional habitat with potentially diverse chemical and physical environments that could support different forms of life. Recent studies suggest that Enceladus's ocean may be highly alkaline, with a pH between 10 and 11.5, significantly more basic than Earth's oceans. This alkalinity could result from the same water-rock interactions that produce the phosphates detected in the plumes, as well as from the loss of carbon dioxide to space through the plume activity itself. While such extreme alkalinity might seem hostile to life, many organisms on Earth thrive in highly alkaline environments. From the bacteria that inhabit soda lakes to the microbes that flourish in deeply buried groundwater systems where similar chemistry prevails. The seasonal variability of the plumes adds another layer of complexity to this already remarkable system. The jets are most active when Enceladus is farthest from Saturn in its slightly elliptical orbit, suggesting that changing tidal stresses control the opening and closing of conduits between the ocean and the surface. This tidal pumping system could serve as a kind of circulation pattern, bringing deep ocean water to the surface where it interacts with Saturn's radiation environment, potentially creating additional chemical compounds that could then be carried back down to the ocean depths. The discovery of complex organic molecules in the plumes, including compounds with molecular weights exceeding 200 atomic mass units, suggests that sophisticated chemistry is occurring in Enceladus's ocean. While these molecules are not direct evidence of life, their presence indicates that the ocean contains the carbon-based building blocks from which biological molecules could potentially assemble. Some of these organics appear to be concentrated in the central regions of the plumes, suggesting they may be originating from specific hydrothermal vents or chemical processes occurring in the ocean depths. As you rest in the quiet of your room, Enceladus continues its ancient dance around Saturn, its hidden ocean stirred by tidal forces that have persisted for billions of years. Every few hours, another pulse of water vapor and ice particles erupts from the tiger stripe fractures, carrying with it the chemical signature of an alien sea that may be among the most habitable environments in our solar system. The plumes climb high into the vacuum of space before falling back to the surface or escaping entirely to feed Saturn's ring system, creating a continuous cycle that makes Enceladus one of the most geologically active worlds we know. The breath of this small moon reaches across millions of miles to touch our instruments and our imagination, carrying with it phosphates and organics, salts and minerals, the very ingredients from which life itself is constructed. In the perpetual darkness of Enceladus's global ocean, chemistry unfolds according to principles that may be universal, following the same fundamental patterns that led to the emergence of biology on Earth billions of years ago. Tonight, as you drift toward sleep, those alien waters continue to flow, warmed by the gravitational embrace of Saturn, enriched by interactions with rock, and perhaps, just perhaps, nurturing forms of life that have adapted to thrive in the hidden seas of our solar system's most surprising moon. Chapter 5: Titan's Liquid Lakes and Orange Haze. Titan, Saturn's largest moon, floats in an orange haze like a dream world painted in sepia tones. You drift through your imagination now into this alien landscape where the familiar processes of Earth unfold with an otherworldly chemistry, where rivers carve valleys not through rock, but through frozen water ice, where rain falls not from clouds of water vapor, but from methane-rich mists, and where vast lakes stretch across polar regions filled not with water, but with liquid hydrocarbons cold enough to freeze your breath solid in an instant. This is perhaps the most Earth-like world in our solar system, yet it operates according to principles of chemistry and physics so foreign that standing on its surface would be like visiting a planet from another dimension, where the very elements that make up rain and rivers have been transformed into something altogether different. The discovery of liquid lakes on Titan represents one of the most remarkable confirmations of theoretical prediction in the history of planetary science. For more than 2 decades before the Cassini spacecraft arrived at Saturn, scientists had speculated that Titan's thick, methane-rich atmosphere might support a complete hydrological cycle, with evaporation, precipitation, and surface flow, creating lakes and rivers of liquid hydrocarbons. The theoretical foundation seems sound. Titan receives enough energy from the distant sun, combined with greenhouse warming from its dense atmosphere, to maintain temperatures that hover right at the threshold where methane can exist as a liquid on the surface. Yet for years, Titan's perpetual orange haze, created by complex organic molecules called tholins that form when methane interacts with sunlight, prevented any direct observation of the surface below. When Cassini finally pierced that haze with radar imaging in July 2006, the moon revealed a landscape that exceeded even the most optimistic scientific predictions. The radar data showed more than 75 dark patches scattered across Titan's northern polar region, ranging from small ponds just a few miles across to vast bodies of liquid larger than Lake Superior. These features showed the unmistakable characteristics of lakes: smooth, radar-dark surfaces that reflected radio waves like mirrors, complete with shorelines, inlet channels, and evidence of changing liquid levels that spoke of an active, dynamic hydrological system operating according to seasonal cycles driven by Saturn's 29-year orbit around the Sun. The three largest bodies of liquid on Titan have been designated as Maria, seas in the astronomical tradition, with names that evoke the mythological creatures of the deep. Kraken Mare, the largest, stretches across an area roughly the size of the Caspian Sea, while Ligeia Mare and Punga Mare complete the triumvirate of Titan's great hydrocarbon oceans. These seas exist primarily in Titan's northern hemisphere, where the longer summer season allows liquid methane to accumulate in permanent reservoirs rather than evaporating back into the atmosphere. Bathymetric analysis using radar reflections from the seafloor reveals that some of these lakes reach depths of over 650 feet, creating three-dimensional liquid environments that could potentially support complex chemistry across a range of depths and pressures. The seasonal cycle that drives Titan's methane weather operates on a scale that dwarfs Earth's climate patterns. As Saturn completes its lengthy orbit around the Sun, each season on Titan lasts roughly 7 Earth years, creating long periods of warming and cooling that drive massive transfers of liquid between the hemispheres. During the northern spring and summer, which lasted from 2009 to 2017, Cassini observed dramatic changes in the brightness and extent of the polar lakes, with some features appearing to fill while others partially emptied. Computer models suggest that this seasonal transport involves the evaporation of liquid methane from warmer regions near Titan's equator, followed by atmospheric circulation that carries the vapor to the colder polar regions, where it condenses and falls as methane rain, filling the lakes and seas through processes remarkably similar to Earth's water cycle. Yet Titan's surface liquids are not simply methane. Spectroscopic analysis reveals a complex cocktail of hydrocarbons, with ethane playing an increasingly important role as the atmosphere's methane is gradually processed by solar radiation and converted into longer chain molecules. This ongoing chemical transformation should theoretically result in the accumulation of vast ethane oceans hundreds of meters deep. Yet the observed lakes contain only a fraction of the ethane that models predict should have accumulated over Titan's geological history. The mystery may be solved by the discovery of what scientists believe to be hydrocarbon wetlands, regions where liquid hydrocarbons percolate into the subsurface, creating underground reservoirs analogous to groundwater aquifers on Earth. These subsurface hydrocarbon systems may be among the most chemically interesting environments in the solar system. As liquid methane and ethane interact with Titan's ice rock subsurface, complex chemical reactions could produce a variety of organic compounds under conditions of pressure and temperature that favor the formation of larger, more complex molecules. Some scientists have proposed that this underground chemistry might even support forms of life based on entirely different biochemistry than anything found on Earth. Organisms that use liquid methane as a solvent rather than water, and that derive energy from chemical reactions involving the abundant organic compounds that rain down from Titan's atmosphere. The possibility of methane-based life on Titan challenges our most fundamental assumptions about the requirements for biology. On Earth, all known life uses water as its primary solvent, relying on water's unique properties to dissolve nutrients, transport waste products, and maintain the complex molecular structures necessary for cellular processes. But recent laboratory studies have demonstrated that many of the chemical reactions essential for life could theoretically occur in liquid methane, albeit at much slower rates due to the extreme cold. Complex organic molecules, including some that might serve as genetic material, remain stable in methane at temperatures around negative 290 degrees Fahrenheit, suggesting that an entirely different form of biochemistry could potentially evolve in Titan's hydrocarbon-rich environment. The evidence for active chemistry in Titan's lakes continues to accumulate as scientists analyze data from Cassini's extended mission. Seasonal changes in the composition and extent of the lakes suggest ongoing chemical processes that go beyond simple evaporation and condensation. Some lakes show evidence of floating or suspended material that could represent complex organic precipitates, solid compounds that form when dissolved molecules in the liquid hydrocarbons reach saturation levels. The shorelines of some lakes display terraced features that might indicate changing liquid levels over time, while other bodies show smooth, steep edges that suggest active erosion by waves or currents. Recent computational modeling has suggested that Titan's lakes might even experience something analogous to weather, with waves driven by wind creating surf that laps against hydrocarbon beaches. The moon's thick atmosphere can generate winds of up to 50 miles per hour during seasonal transitions, potentially creating wave action that could erode shorelines and transport sediments in patterns similar to those observed in Earth's coastal environments. Standing at the edge of Ligea Mare, an observer might witness methane waves crashing against shores of water ice rock, beneath an orange sky, where methane clouds drift through an atmosphere 4 times denser than Earth's. The organic chemistry occurring in Titan's lakes represents a natural laboratory for prebiotic chemistry, the formation of complex molecules that might serve as precursors to life. The constant influx of organic compounds from the atmosphere, combined with the chemical energy available from seasonal temperature changes and potential tidal heating from Saturn's gravity, creates conditions where increasingly complex molecules could form and accumulate over geological timescales. Some of these compounds, including nitriles and amino acids, have been detected in laboratory experiments designed to simulate Titan's surface chemistry, suggesting that the moon's lakes might be actively synthesizing some of the building blocks necessary for biological processes. NASA's upcoming Dragonfly mission, scheduled to launch in 2027, will provide our first direct exploration of Titan's surface chemistry. This nuclear-powered rotorcraft will hop across the moon's landscape, sampling the organic deposits that accumulate around the lake shores and analyzing the chemical composition of the atmosphere and surface materials. The mission is specifically designed to search for signs of prebiotic chemistry and potentially even metabolic processes that might indicate the presence of exotic forms of life adapted to Titan's hydrocarbon-rich environment. As you rest in the warmth of your bed, Titan continues its slow rotation beneath Saturn's pale glow, its methane lakes stirred by winds that carry the complex organic molecules synthesized high in the atmosphere down to the surface, where they accumulate in an ever-thickening layer of prebiotic chemistry. The seasonal rains continue to fall, not water, but liquid methane, filling lakes that have never known the touch of sunlight directly, creating chemical environments so alien, yet so tantalizingly similar to the conditions where life might first emerge, that they represent some of our best opportunities to answer whether biology is a cosmic accident or a fundamental property of chemistry itself. Tonight, in the orange twilight of a world 750 million miles from Earth, chemistry unfolds according to rules we are only beginning to understand, in lakes that might be cradles for forms of life as different from us as we are from the rocks beneath our feet. Chapter 6: The Volcanic Moons and Underground Rivers. You float now through the quiet darkness between worlds, where gravitational forces play a cosmic symphony of heat and motion that transforms frozen moons into active, dynamic worlds, harboring the potential for life. Beyond the familiar names of Europa and Enceladus, Jupiter and Saturn host entire families of moons, where liquid water flows in hidden depths, where volcanic forces shape landscapes and warm subsurface oceans, and where the delicate interplay between orbital mechanics and internal geology creates environments that might support biology in forms we are only beginning to imagine. Tonight, as you rest in the gentle embrace of your bed, we explore these lesser-known worlds where fire and ice dance together in the perpetual twilight of the outer solar system. Ganymede, Jupiter's largest moon, and indeed the largest moon in our entire solar system, presents a paradox wrapped in ice and rock. Larger than the planet Mercury, yet composed of roughly equal parts rock and water ice, this massive world has long puzzled scientists with its complex surface geology and mysterious magnetic field. Unlike its smaller sibling Europa, Ganymede displays two distinct types of terrain that tell a story of ancient geological upheaval and ongoing internal activity. The darker, more heavily cratered regions speak of a surface that formed over 4 billion years ago, scarred by eons of asteroid and comet impacts in the violent early epochs of solar system history. But interspersed with these ancient lands are lighter, grooved terrains that show clear evidence of more recent geological activity, parallel ridges and valleys that stretch for hundreds of kilometers, suggesting that something beneath Ganymede's icy surface has been reshaping the moon's landscape from within. The key to understanding Ganymede's hidden activity lies in its unique magnetic field, the only moon in our solar system known to generate its own magnetosphere. This magnetic shield, while much weaker than Earth's, creates aurora displays that dance around Ganymede's poles in ribbons of ultraviolet light that can be detected by the Hubble Space Telescope from over 400 million miles away. These auroras provided scientists with an unexpected tool for peering beneath Ganymede's icy surface, because their behavior is influenced not only by Ganymede's own magnetic field, but also by Jupiter's much more powerful magnetosphere that engulfs the moon as it orbits through the giant planet's magnetic domain. When researchers carefully tracked the movement of Ganymede's auroral belts over time, they discovered something remarkable. The auroras exhibited a subtle rocking motion that could only be explained by the presence of a substantial layer of electrically conductive material within the moon's interior. Since pure ice is not conductive, this hidden conductor had to be salt water, a vast subsurface ocean that deflects and modifies Jupiter's magnetic field as it sweeps past Ganymede during the moon's 7-day orbital period. The magnetic signature revealed an ocean that may contain more water than all of Earth's surface seas combined, sandwiched between layers of different ice phases at depths ranging from perhaps 150 to 250 kilometers beneath the surface. This discovery places Ganymede in the exclusive club of confirmed ocean worlds, but its internal structure may be far more complex than the relatively simple ice shell over ocean model that applies to Europa and Enceladus. Computer models of Ganymede's interior suggest that the extreme pressure at depth creates multiple layers of different ice phases, potentially resulting in a stack of several separate ocean layers separated by barriers of high-pressure ice. These layered oceans could create distinct chemical environments within the same moon, each with different temperatures, pressures, and chemical compositions that might support different forms of life or prebiotic chemistry. The deepest ocean layer, in direct contact with Ganymede's rocky mantle at depths approaching 800 kilometers, represents perhaps the most intriguing environment from an astrobiological perspective. Here, water-rock interactions could drive hydrothermal chemistry similar to that occurring on Earth's ocean floors, but under pressure conditions and over timescales that have no terrestrial analog. The immense weight of nearly 800 kilometers of overlying ice and water could create temperatures at the ocean floor that are 40 degrees warmer than at the ice-water boundary above, potentially driving convection currents that transport heat and chemicals throughout this deep ocean system. Recent analysis of Juno spacecraft data has revealed that Ganymede's surface bears the chemical fingerprints of this hidden ocean activity. Spectroscopic observations have detected various salts and other compounds scattered across the Moon's surface, including hydrated sodium chloride, ammonium chloride, sodium bicarbonate, and possibly organic aldehydes. These compounds appear to be most abundant at Ganymede's lower latitudes, regions that are partially shielded from Jupiter's intense radiation by the Moon's magnetic field. The distribution pattern suggests that these materials may have been deposited during past episodes of geological activity when subsurface ocean water reached the surface, perhaps through the same processes that created the light, grooved terrain that covers much of Ganymede's surface. Moving inward toward Jupiter, we encounter Io, a world that represents the extreme endpoint of tidal heating in our solar system. This moon, slightly larger than Earth's moon, experiences gravitational forces so intense that its entire interior remains molten, making it the most volcanically active body known to science. While Io's surface conditions are far too extreme for liquid water to exist, its incredible geological activity demonstrates the power of tidal forces to generate heat and drive chemical processes that could operate within the more protected interiors of other moons. The sulfur compounds that paint Io's surface in brilliant yellows, oranges, and reds are constantly recycled through volcanic processes that represent some of the most energetic chemistry occurring anywhere in the solar system. Yet even in Jupiter's radiation-scorched inner system, surprises await. Recent studies have suggested that Io may have influenced the evolution of its neighboring moons in ways that could affect their habitability. The volcanic moon's constant outgassing contributes to Jupiter's magnetosphere and may have helped create the radiation environment that shapes the surface chemistry of Europa and Ganymede. This interconnected system of moons demonstrates how the search for life must consider not just individual worlds, but entire systems of gravitationally and chemically linked bodies. In Saturn's system, beyond the headline-grabbing discoveries at Enceladus and Titan, a host of smaller moons harbor their own secrets. Mimas, famous for its resemblance to the Death Star from Star Wars due to a massive impact crater, has recently been discovered to harbor a subsurface ocean despite its small size and inactive appearance. This finding suggests that liquid water may be far more common in the outer solar system than previously thought, hidden beneath the surfaces of moons that show no obvious signs of geological activity. Dione, another of Saturn's mid-sized moons, displays wispy features across its surface that may represent sites where water vapor has erupted from subsurface reservoirs, similar to, but much fainter than the dramatic plumes of Enceladus. The Cassini spacecraft detected a thin oxygen atmosphere around Dione, possibly generated by the breakdown of water molecules exposed to Saturn's radiation environment, hinting at subsurface water reservoirs that occasionally reach the surface through geological processes we are only beginning to understand. Even more distant and enigmatic is Triton, Neptune's largest moon and the only large moon in the solar system that orbits in a retrograde direction, suggesting it may be a captured Kuiper Belt object. Despite being located in the frozen outer reaches of the solar system, where sunlight provides almost no heating, Triton displays active nitrogen geysers that shoot dark material hundreds of kilometers into its thin atmosphere. The energy source for this activity remains mysterious, but tidal heating from Neptune's gravity, combined with possible radioactive decay within Triton's interior, might maintain subsurface liquid reservoirs that could potentially support microbial life. These volcanic and tidally heated moons represent natural laboratories where we can study the processes that generate and maintain subsurface oceans throughout the solar system. Each world offers a different combination of size, composition, orbital dynamics, and geological history, creating a spectrum of environments that could potentially support life under conditions ranging from the familiar chemistry of liquid water to exotic biochemistries adapted to high pressure, extreme cold, or unusual chemical compositions. The discovery that so many moons in the outer solar system harbor subsurface oceans has fundamentally changed our understanding of habitability in the universe. No longer must we restrict our search for life to the narrow Goldilocks zone around stars, where liquid water can exist on planetary surfaces. Instead, we now recognize that tidal heating can maintain liquid water environments throughout solar systems, potentially making habitable worlds far more common than we ever dared hope. As you drift towards sleep, your mind filled with images of hidden oceans and volcanic eruptions illuminating alien skies, consider that above you in the night sky, these distant worlds continue their ancient orbital dances, their interiors warmed by the gravitational embrace of giant planets, their subsurface seas stirred by tidal forces that have persisted for billions of years. In the perpetual darkness of these hidden oceans, life may have found ways to thrive that exceed our wildest imagination, adapting to environments that represent some of the most stable and long-lived habitable zones in the solar system. Tonight, as volcanic plumes rise into the vacuum of space and tidal currents flow through ocean depths that have never known starlight, the search for life continues in places where fire and ice have learned to coexist in the gentle choreography of celestial mechanics. Chapter 7. The Chemistry of Hidden Life. Life leaves fingerprints, chemical signatures that scientists call biosignatures. You drift through this concept now as you rest in the gentle quiet of your room, imagining how we detect the invisible, studying the gases that living things produce, the isotope ratios that tell stories of metabolism, and the complex molecules that don't form naturally in sterile environments. The search for alien life in our solar system has become an exercise in cosmic forensics, where researchers must learn to read the subtle chemical language written in atmospheres, ice, and rock by processes that might indicate the presence of biology operating according to principles both familiar and utterly foreign to our terrestrial experience. The challenge of detecting life beyond Earth begins with the fundamental question of what constitutes a biosignature, a chemical or physical feature that provides evidence of past or present biological activity. On Earth, life has transformed our planet's atmosphere over billions of years, creating chemical combinations that would be impossible to maintain without constant biological intervention. The oxygen we breathe exists in our atmosphere only because photosynthetic organisms continuously produce it at rates that far exceed natural processes that would otherwise consume it. Without life, Earth's atmosphere would contain virtually no free oxygen, as this highly reactive gas would quickly combine with rocks and other materials to form oxides and other compounds. This principle of chemical disequilibrium, the presence of gases or other compounds that shouldn't exist together in significant quantities without active processes to maintain them, forms the foundation for how we search for life throughout the solar system. When the Hubble Space Telescope detects water vapor plumes erupting from Europa's surface, scientists immediately begin analyzing the chemical composition of those plumes for signs of biological activity. The presence of certain organic compounds, unusual isotope ratios, or chemical combinations that require active maintenance could all potentially indicate that biological processes are occurring in Europa's hidden ocean. Recent discoveries have revealed that the chemistry of life in our solar system may be far more complex and varied than we initially imagined. The detection of phosphine in Venus's atmosphere created worldwide excitement in 2020 because this gas, on Earth, is almost exclusively produced by anaerobic microorganisms, bacteria that thrive in oxygen-free environments like swamps, marshes, and the intestines of animals. While subsequent analysis has raised questions about the initial phosphine detection and alternative non-biological explanations have been proposed, the discovery highlighted how a single molecular signature could potentially indicate the presence of life in one of the most hostile environments in the solar system. The search for biosignatures on Mars has revealed a tantalizing array of chemical puzzles that continue to challenge our understanding of what constitutes evidence for life. The seasonal variations in methane detected in the Martian atmosphere represent one of the most intriguing potential biosignatures discovered to date. On Earth, roughly 90% of atmospheric methane is produced by biological processes, from the digestion of plant matter by bacteria in wetlands to the metabolic processes of various microorganisms. The fact that Martian methane levels appear to fluctuate with the seasons, increasing during warmer periods and decreasing in winter, suggests an active source that could potentially be biological. But methane production on Mars, if it exists, would necessarily involve very different biology than what we observe on Earth. The red planet's thin atmosphere and harsh radiation environment would require any methane-producing organisms to exist deep underground, possibly in subsurface aquifers, or protected cave systems where they could access liquid water and derive energy from chemical reactions involving minerals in the rock. These organisms might belong to a group called methanogens, archaea, that produce methane as a byproduct of their metabolism, and that represent some of the most ancient forms of life on Earth. The complexity of interpreting potential biosignatures becomes even more apparent when we consider the organic molecules discovered in Martian rocks by NASA's rovers. The Curiosity rover has detected a variety of organic compounds in sedimentary rocks that formed in ancient lake beds, including thiophanes, benzene, toluene, and small carbon chains that could serve as building blocks for more complex biological molecules. While these compounds can form through non-biological processes, their diversity and abundance in rocks that formed in environments that once contained liquid water make them tantalizing hints of possible past biological activity. Perhaps even more intriguing is the discovery of seasonal variations in the abundance of organic molecules in Martian rocks. As temperatures change throughout the Martian year, the release of organic compounds from rock samples also varies, suggesting that these molecules are not simply ancient contaminants, but may be part of an active chemical system that responds to environmental conditions. Some scientists have proposed that this seasonal cycling could indicate the presence of extant microbial life that becomes more active during warmer periods, releasing organic compounds that can be detected by rover instruments. The moons of the outer solar system present their own unique challenges for biosignature detection, as any life in these environments would necessarily be adapted to conditions radically different from those found on Earth. The subsurface oceans of Europa, Enceladus, and Ganymede exist in perpetual darkness, at temperatures well below freezing at the surface, under pressures that would crush most terrestrial organisms, and in chemical environments that may be highly alkaline or acidic. Yet these same extreme conditions could favor the evolution of exotic biochemistries that might produce biosignatures unlike anything we would recognize from Earth-based biology. The water vapor plumes erupting from Enceladus provide a direct window into the chemistry of that moon's subsurface ocean, carrying with them a complex mixture of water, salt, organic compounds, and potentially even microscopic ice particles that could preserve biological materials from the ocean depths. When NASA's Cassini spacecraft flew through these plumes, it detected complex organic molecules with molecular weights exceeding 200 atomic mass units, compounds that approach the complexity of simple proteins or nucleic acids. While these molecules could form through non-biological chemistry, their presence in an environment that also contains liquid water, energy sources, and essential elements like phosphorus creates conditions that could potentially support biological processes. The challenge of distinguishing between biological and non-biological sources for these complex organic molecules represents one of the most difficult aspects of astrobiology. Many of the chemical signatures we associate with life on Earth can also be produced by geological processes, chemical reactions driven by radiation, or the complex organic chemistry that occurs in space itself. For example, amino acids, the building blocks of proteins, have been found in meteorites and comets, formed through purely chemical processes in the absence of any biological activity. This ambiguity has led astrobiologists to focus not just on individual molecules, but on patterns of chemistry that might be difficult to explain without biological processes. Life on Earth exhibits strong preferences for certain molecular structures over others, creating what scientists call homochirality, the tendency for biological systems to use only left-handed amino acids and right-handed sugars, even though both mirror image forms of these molecules can be produced by non-biological chemistry. The detection of similar molecular preferences in samples from Mars, Europa, or other potentially habitable worlds could provide strong evidence for biological activity. Another approach involves looking for chemical signatures that indicate metabolism, the complex network of chemical reactions that living organisms use to extract energy from their environment and build the molecules necessary for growth and reproduction. Metabolic processes often leave distinctive isotopic signatures, as biological systems tend to preferentially use lighter isotopes of elements like carbon, sulfur, and nitrogen. These preferences can create measurable differences in the ratios of different isotopes in biological versus non-biological materials, providing a potential tool for detecting past or present life even in samples that no longer contain intact biological structures. The search for biosignatures must also account for the possibility that life in other environments might use completely different biochemistry than terrestrial organisms. While all known life on Earth is based on carbon chemistry and uses water as a solvent, theoretical studies suggest that other forms of biochemistry might be possible under different conditions. Silicon-based biochemistry, for example, might be stable at the high temperatures found in some volcanic environments, while biochemistry based on liquid methane or ammonia might operate at the extremely low temperatures found on Titan or other outer solar system bodies. As you rest in the darkness of your room, consider that at this very moment, robotic explorers throughout the solar system are conducting the most sophisticated search for biosignatures ever attempted. The Perseverance rover on Mars is collecting samples that will eventually be returned to Earth for analysis, with instruments far more sensitive than anything that can be sent to other planets. The Europa Clipper mission will taste the plumes erupting from that moon's surface, searching for chemical signatures that could indicate biological activity in the hidden ocean below. Future missions to Enceladus, Titan, and other potentially habitable worlds will expand this search to environments that might harbor forms of life unlike anything we can currently imagine. The chemistry of hidden life may be written in languages we are only beginning to learn to read, expressed through molecular signatures that speak of metabolic processes adapted to conditions of eternal darkness, extreme cold, crushing pressure, or chemical environments that would be toxic to terrestrial organisms. Yet beneath these alien chemistries may lie the same fundamental patterns that govern all living systems: the extraction of energy from the environment, the construction of complex structures from simple building blocks, and the storage and transmission of information necessary for growth, reproduction, and evolution. Tonight, as you drift toward sleep, that hidden chemistry continues its ancient work in the depths of alien oceans, possibly writing the signatures of life in molecules that float through subsurface seas, waiting to be discovered by instruments sensitive enough to detect the whispered presence of biology in the vast, patient darkness of our solar system. Chapter 8: The Deep Time of Panspermia. Perhaps life didn't begin separately on different worlds, but traveled between them, riding on meteorites blasted from planetary surfaces by cosmic impacts. You drift through this concept now as you rest in your bed, imagining microscopic travelers journeying through space, sleeping in the cold vacuum for millions of years before awakening on a new world. This is panspermia, the idea that life might spread throughout the solar system, not by arising independently on each world, but by being transferred from one planet or moon to another through the slow, patient process of cosmic billiards that has been reshaping our solar system since its earliest days. The concept of panspermia challenges our most fundamental assumptions about the origin and distribution of life in the universe. Rather than requiring the unlikely event of abiogenesis, the spontaneous emergence of life from non-living matter, to occur multiple times throughout the solar system, panspermia suggests that life might have originated only once, then spread to populate multiple worlds through natural processes that operate on cosmic timescales. This possibility has profound implications for how we understand the relationship between Earth and other potentially habitable environments in our cosmic neighborhood, suggesting that any life we discover on Mars, Europa, or other worlds might be our distant relatives, sharing common ancestors that date back billions of years to the earliest epochs of solar system history. The mechanism by which panspermia might operate became clear only when scientists began to understand the violent dynamics of the early solar system, particularly during the period known as the Late Heavy Bombardment, which occurred roughly 4.1 to 3.8 billion years ago. During this chaotic epoch, massive asteroids and comets pummeled the inner planets with unprecedented fury, excavating enormous craters and launching vast quantities of material into space. When a large asteroid or comet strikes a planetary surface at cosmic velocities, the energy released can exceed that of the most powerful nuclear weapons, creating shock waves that propagate through the planet's crust and eject debris at speeds sufficient to escape the planet's gravitational pull entirely. Computer simulations of these impact events reveal that rocky material blasted from one world can indeed reach other planets, following complex orbital trajectories that may take millions of years to complete. The exchange is most efficient between worlds that are relatively close to each other, particularly between Mars and Earth, which orbit at distances that make material transfer not just possible, but inevitable over geological timescales. Studies of Martian meteorites found on Earth demonstrate that this process operates in both directions, with rocks ejected from Mars by asteroid impacts eventually falling to Earth as meteorites after journeys through space that may have lasted tens of millions of years. The discovery of Martian meteorites on Earth provided the first concrete evidence that panspermia might be more than just theoretical speculation. These rocks, identified by their distinctive chemical and isotopic signatures that match the composition of the Martian atmosphere as measured by spacecraft, represent actual samples of Mars that have made the journey from one world to another through purely natural processes. More remarkably, some of these Martian meteorites show evidence of having been ejected from Mars during relatively recent geological periods, suggesting that the exchange of material between planets continues to this day, albeit at much lower rates than during the chaotic early epochs of solar system history. The survival of potential microbial passengers during these interplanetary voyages represents one of the most challenging aspects of panspermia theory. Space is an extraordinarily hostile environment for biological organisms, with temperatures approaching absolute zero, vacuum conditions that would instantly boil away any liquid water, and radiation levels that can destroy cellular structures and genetic material. However, laboratory studies have demonstrated that certain types of microorganisms, particularly bacterial spores and extremophile organisms adapted to harsh conditions, can survive exposure to space-like conditions for remarkably long periods when protected within the interior of rocky meteorites. Recent experiments conducted on the International Space Station have exposed various microorganisms to the vacuum and radiation of space for periods of up to 18 months, finding that some species can indeed survive these extreme conditions when shielded by even minimal amounts of protective material. Bacteria belonging to the genus Deinococcus, known for their extraordinary resistance to radiation, have shown particular resilience in these studies, maintaining viability even after exposure to radiation doses thousands of times higher than would be lethal to most terrestrial organisms. These findings suggest that the interior portions of meteorites might provide sufficient protection for microbial life to survive interplanetary journeys lasting millions of years. The question of whether microorganisms could remain viable during the extremely long transit times required for panspermia becomes even more intriguing when we consider the discovery of ancient microbes in terrestrial environments that have remained dormant for geological periods. Scientists have successfully revived bacterial spores from amber deposits over 100 million years old, and microorganisms have been found in salt crystals and other geological formations that date back hundreds of millions of years. These discoveries demonstrate that life possesses remarkable abilities to enter states of suspended animation that can persist over timescales that dwarf human comprehension, suggesting that the millions of years required for interplanetary travel might not represent an insurmountable barrier to microbial survival. The chemical and isotopic analysis of Martian meteorites has revealed another tantalizing piece of evidence that might support panspermia theory. Some of these rocks show clear signs of having been exposed to liquid water on Mars, with mineral formations and chemical alterations that could only have occurred in aqueous environments. More controversially, a few researchers have claimed to identify microscopic structures within certain Martian meteorites that resemble fossilized microorganisms, though these claims remain highly disputed within the scientific community. The famous ALH 84001 meteorite, discovered in Antarctica in 1984, contains carbonate minerals that formed in the presence of water, along with microscopic structures that some scientists interpret as possible fossilized bacteria, though alternative non-biological explanations for these features have also been proposed. If panspermia has indeed operated throughout solar system history, it would have profound implications for the search for life on other worlds, rather than representing completely independent experiments in abiogenesis. Any microbial ecosystems we might discover on Mars, Europa, or other potentially habitable environments could be the descendants of a single genesis event that occurred billions of years ago, possibly on Earth, Mars, or even in the outer solar system, where organic chemistry might have been more favorable during the early epochs of solar system formation. This possibility suggests that comparative studies of terrestrial and extraterrestrial life might reveal fundamental similarities in biochemistry, genetic codes, and metabolic pathways that reflect their common origin. The implications extend beyond simple relatedness to questions of how life might adapt and evolve when transported to new environments. Microorganisms that successfully made the journey from one world to another would necessarily be among the most resilient and adaptable forms of life, capable of surviving not only the rigors of space travel, but also the challenge of establishing themselves in potentially very different environmental conditions on their new home. These cosmic colonists might retain genetic information from their world of origin while simultaneously adapting to local conditions, creating hybrid ecosystems that reflect both their extraterrestrial heritage and their new planetary environment. The panspermia hypothesis also suggests that the solar system itself might function as a single, interconnected biological system, with life flowing between worlds according to the gravitational dynamics and impact history that shape planetary evolution. This perspective transforms our understanding of planetary habitability from a property of individual worlds to a characteristic of entire solar systems, where the presence of life on one world increases the probability of finding life elsewhere through natural processes of biological dispersal that operate over cosmic timescales. As you drift towards sleep, consider that the very atoms in your body might once have been part of rocks that traveled through space, possibly carrying with them the chemical signatures or even the living descendants of microorganisms that originated on distant worlds. The boundary between Earth and space becomes less distinct when viewed through the lens of panspermia, with our planet existing not as an isolated oasis of life, but as one node in a vast network of potentially connected biospheres that extends throughout the solar system. Tonight, as meteorites continue to fall silently to Earth's surface, they might be carrying more than just rock and metal. They might be bringing home distant relatives whose ancestors began their cosmic journey millions of years ago on worlds that orbit the same sun that now illuminates your dreams of life among the stars. The patient process of panspermia continues to operate in the quiet depths of space, where rocky fragments ejected from planetary surfaces millions of years ago continue their long journeys between worlds, possibly carrying within their protective interiors the dormant seeds of life that could one day awaken on alien shores, ready to begin the next chapter in biology's cosmic story. Chapter 9. The search continues in gentle patience. The search for life in our solar system unfolds with the patience of deep time. You float alongside the spacecraft and rovers that serve as our gentle ambassadors, slowly gathering evidence, sampling ice, analyzing atmosphere, drilling into ancient rocks. As you rest in the quiet comfort of your room, missions launched years ago continue their methodical work across millions of miles of space. Their instruments, designed not for quick answers, but for the careful accumulation of data that might one day reveal the presence of biology in the most unexpected places. This is science at its most patient and persistent, a testament to humanity's willingness to invest decades in the pursuit of answers to questions that have haunted our species since we first looked up at the night sky and wondered if we are alone. The Europa Clipper mission, launched in October 2024, represents the culmination of decades of planning and technological development aimed at exploring one of the most promising environments for life in our solar system. This spacecraft, larger than a basketball court when its solar arrays are deployed, carries 9 sophisticated instruments designed to map Europa's hidden ocean from orbit without ever landing on the moon's surface. The mission's approach embodies the gentle philosophy of modern astrobiology. Rather than attempting to drill through Europa's ice shell or land directly on its surface, Europa Clipper will conduct repeated flybys, each one bringing different instruments to bear on specific questions about the moon's habitability. The spacecraft's ice-penetrating radar will peer through Europa's frozen shell to map the boundaries of the liquid ocean below, revealing its depth, salinity, and potentially even detecting areas where the ocean comes closer to the surface through upwelling currents or geological activity. Meanwhile, spectrometers will analyze the chemistry of Europa's tenuous atmosphere and any water vapor plumes that might be erupting from the surface, searching for the molecular signatures that could indicate biological processes occurring in the hidden sea below. The mission's magnetometer will refine our understanding of Europa's subsurface ocean by precisely measuring the magnetic field variations that reveal the presence of electrically conductive saltwater. Perhaps most intriguingly, Europa Clipper carries a thermal imager capable of detecting warm areas on Europa's surface that might indicate recent geological activity, or locations where the subsurface ocean has influenced surface temperatures. These warm spots could represent the most promising targets for future missions designed to sample or even drill through the ice to directly access the ocean below. The patient accumulation of data from dozens of flybys over several years will create the most detailed picture of Europa ever obtained, providing the foundation for planning future missions that might finally answer whether life exists in this alien sea. Simultaneously, the Dragonfly mission prepares for its 2027 launch to Titan, representing an entirely new approach to exploring potentially habitable environments in the outer solar system. Rather than orbiting or landing in a single location, this nuclear-powered rotorcraft will hop across Titan's landscape like an enormous mechanical dragonfly, sampling different environments and searching for signs of prebiotic chemistry, or potentially even exotic forms of life adapted to the Moon's hydrocarbon-rich environment. The mission duration of over 2 years will allow Dragonfly to explore multiple sites, from the organic dunes near Titan's equator to the margins of the hydrocarbon lakes in the polar regions, building a comprehensive understanding of the Moon's chemical evolution and potential for supporting biology. The gentle persistence of these missions reflects a fundamental shift in how we approach the search for life beyond Earth. Rather than expecting dramatic discoveries announced in press conferences, astrobiologists have learned to read the subtle signatures that life leaves in its environment. Chemical disequilibria that suggest active biological processes, isotopic ratios that hint at metabolic activity, seasonal variations in atmospheric composition that could indicate living systems responding to environmental changes. The search unfolds through the patient analysis of spectra, the careful comparison of chemical compositions, the statistical analysis of data collected over years or even decades of observations. On Mars, this patient approach has already begun to yield tantalizing results. The Perseverance rover continues its methodical exploration of Jezero crater, collecting samples that will eventually be returned to Earth for analysis with instruments far more sophisticated than anything that can be transported to another planet. Each sample represents a potential window into Mars's biological history, carefully selected based on geological context, chemical composition, and the likelihood of preserving biosignatures if they exist. The Mars Sample Return mission, planned for the early 2030s, will bring these precious specimens back to Earth, where they can be analyzed by teams of researchers using the most advanced techniques available to science. The search for life has also expanded to include missions that weren't originally designed for astrobiology, but have revealed unexpected insights into the habitability of our solar system. The Juno mission to Jupiter has provided new understanding of the giant planet's magnetosphere and its effects on the potentially habitable moons, while the Cassini mission's extended exploration of the Saturn system revealed not just the active plumes of Enceladus, but also evidence for subsurface oceans on several other moons that were previously thought to be geologically dead. Future missions under development promise to extend this gentle search even further into the outer solar system. The proposed Enceladus Orbolander would combine orbital observations with direct sampling of the Moon's surface and plumes, potentially detecting biological molecules if they exist in the subsurface ocean. Missions to Uranus and Neptune, being considered for the 2030s, might reveal whether the ice giants host their own systems of potentially habitable moons, extending the search for life to the most distant reaches of our solar system. The technological capabilities required for these missions push the boundaries of engineering and materials science. Instruments must operate reliably in environments where temperatures approach absolute zero. Radiation levels would quickly kill unprotected humans, and communication delays with Earth can exceed several hours. The gentle patience required for these missions extends not just to the scientific observations themselves, but to the decades of technological development required to create instruments capable of detecting the faint signatures of life across millions of miles of space. Advances in artificial intelligence and machine learning are beginning to revolutionize how we analyze the vast quantities of data returned by these missions, rather than requiring human scientists to examine every spectrum or image individually. AI systems can be trained to recognize patterns that might indicate biological processes, flagging potentially interesting observations for more detailed analysis. These tools are particularly valuable for missions like Europa Clipper, which will return terabytes of data that would take human researchers decades to analyze using traditional methods. The integration of multiple datasets from different missions and instruments represents another frontier in the search for life. By combining information from orbital observations, surface rovers, laboratory analysis of meteorites, and theoretical modeling, researchers can build increasingly sophisticated understanding of how biological processes might manifest in different environments. This systems approach recognizes that the signature of life might not be found in any single measurement, but in the patterns that emerge from the careful integration of multiple lines of evidence. As you rest in the gentle darkness of your room, these robotic explorers continue their patient work across the solar system. Europa Clipper cruises through space on its 6-year journey to Jupiter, its instruments powered down, but its trajectory precisely calculated to arrive at the perfect moment to begin its survey of Europa's hidden ocean. On Mars, rovers pause in the Martian night, their nuclear power sources providing enough warmth to keep critical systems alive through temperatures that would freeze carbon dioxide solid, ready to resume their methodical exploration when the alien sun rises again. The search for life unfolds with the patience of geology, the persistence of evolution, and the gentle hope that somewhere in the cosmos, biology has found ways to adapt and thrive in environments we can barely imagine. Each measurement, each sample, each carefully planned observation adds another piece to the vast puzzle of whether we are alone, building toward a moment of discovery that may come tomorrow or may require decades more of careful, patient observation. Tonight, as you drift toward sleep, that gentle search continues in the silence of space, guided by curiosity, powered by human ingenuity, and sustained by the deep patience required to answer the most profound questions we can ask about our place in the universe. Chapter 10: The Quiet Certainty of Connection. As your breathing slows and your thoughts drift like dust motes in starlight, you realize that the search for life is really a search for connection, for the quiet certainty that we're part of something larger. Whether we find microbes in Martian caves, strange chemistry in Titan's lakes, or thriving ecosystems beneath Europa's ice, the discovery will change not just science, but our understanding of home. Tonight, as you rest in the knowledge that the universe is patient with its secrets, revealing them slowly to those who watch and wait and wonder, we explore what it might mean for humanity to finally receive that cosmic telegram we've been hoping for. The confirmation that life exists beyond our pale blue dot. The moment of discovery, when it comes, might unfold not with fanfare, but with quiet certainty. The way morning light slowly illuminates a familiar landscape and reveals details that were always there, but hidden in darkness. Perhaps it will be a graduate student analyzing spectral data from Europa Clipper, noticing chemical signatures in the moon's plumes that can only be explained by biological processes. Or maybe a team of researchers examining samples returned from Mars will find fossilized structures that unmistakably point to ancient microbial communities. The discovery might even emerge from artificial intelligence systems trained to recognize patterns in vast data sets, flagging anomalies that human eyes would never have caught among the millions of measurements accumulated over decades of patient exploration. Whatever form it takes, the confirmation of alien life will represent a watershed moment in human consciousness, fundamentally altering our relationship with the cosmos and our understanding of our place within it. The philosophical implications will ripple through every aspect of human thought, from religion and ethics to law and economics. If life emerges naturally wherever conditions allow, as the discovery of even simple microbes would suggest, then the universe becomes not just a vast collection of stars and planets, but a living system where biology is as fundamental as physics and chemistry. This realization would transform our conception of Earth from a unique oasis to one example of a common phenomenon, a recognition that would be both humbling and profoundly comforting. The scientific revolution that would follow such a discovery would dwarf the impact of any previous breakthrough in our understanding of life. Comparative biology would suddenly expand beyond terrestrial organisms to include alien life forms that might operate according to entirely different biochemical principles. If Martian microbes share common ancestry with terrestrial life through panspermia, they could provide unprecedented insights into the earliest stages of biological evolution, representing a fossil record that extends back billions of years to the very origins of life in our solar system. Alternatively, if alien life represents an independent genesis, it would demonstrate that biology follows universal principles that transcend the specific chemistry of Earth's biosphere. The discovery of life in the subsurface oceans of Europa, Enceladus, or other icy moons would prove that habitable environments are far more common in the universe than we previously imagined. These hidden biospheres, sustained by energy sources completely independent of stellar radiation, could exist throughout the galaxy in star systems of all ages and compositions. The implications for the Drake equation, the famous formula that estimates the number of communicating civilizations in our galaxy, would be staggering, suggesting that life-bearing worlds might number in the billions rather than the thousands, and that intelligence might be far more common than our current Earth-centric perspective suggests. The technological benefits of studying alien life could accelerate human development in ways we can barely imagine. Organisms adapted to the extreme conditions of space might provide blueprints for biotechnology that could help humans survive and thrive in the harsh environments we encounter as we expand beyond Earth. Microbes that thrive in high radiation environments could inspire new approaches to cancer treatment or protection against cosmic radiation during interplanetary travel. The unique biochemistry of life forms, adapted to liquid methane or other exotic solvents, might lead to industrial processes that operate under conditions previously thought impossible for biological systems. Yet perhaps the most profound impact would be psychological and spiritual rather than scientific or technological. The loneliness that has characterized human existence since we first realized the vastness of the cosmos would be replaced by a sense of cosmic companionship, a recognition that life is not rare and precious in its singularity, but abundant and creative in its diversity. This shift in perspective might fundamentally alter how we treat our own planet and each other, fostering a sense of cosmic citizenship that transcends national, cultural, and species boundaries. The ethical frameworks that would emerge from the discovery of alien life would challenge many of our most basic assumptions about moral consideration and environmental protection. If microbes on Mars represent independent evolutionary lineages billions of years in the making, what obligations do we have to protect them from contamination by terrestrial organisms? The planetary protection protocols that already guide space missions would become not just technical requirements, but moral imperatives, ensuring that our exploration of other worlds doesn't inadvertently destroy the very life we seek to understand. Educational systems worldwide would need to be fundamentally restructured to incorporate the new understanding of life's cosmic context. Children would grow up with a radically different conception of their place in the universe, seeing themselves not as isolated inhabitants of a unique world, but as part of a cosmic community of living systems that extends throughout the galaxy. This perspective might foster environmental consciousness and scientific literacy in ways that purely terrestrial examples never could, making abstract concepts like evolution, ecology, and biochemistry immediately relevant to humanity's cosmic future. The search for more complex life and potentially even intelligence would inevitably intensify following the discovery of any alien microbes. If simple life exists on multiple worlds within our own solar system, the statistical likelihood of more complex life elsewhere in the galaxy becomes almost certain. The technologies we develop to study microbial aliens, advanced life detection instruments, sample return capabilities, robotic exploration systems, would provide the foundation for even more ambitious missions to study potentially habitable exoplanets or search for technosignatures from advanced civilizations. Religious and spiritual traditions would face the challenge of incorporating alien life into their worldviews, leading to theological developments that could reshape human spirituality for millennia to come. Some faith traditions might see alien life as confirmation of the universality of creation, while others might struggle to reconcile the existence of non-terrestrial life with doctrines developed in a pre-scientific era. New forms of cosmic spirituality might emerge, based on humanity's newfound understanding of life as a universal phenomenon rather than a terrestrial accident. The economic implications of discovering alien life could be equally transformative. New industries would emerge around the study, protection, and potentially even the cultivation of alien organisms. Space tourism might shift from simply visiting other worlds to observing alien ecosystems, creating entirely new categories of experience that would be available only beyond Earth. The biotechnology sector could be revolutionized by insights gained from studying life forms that evolved under completely different selective pressures than terrestrial organisms. International cooperation in space exploration would likely intensify as nations recognize that the study of alien life requires resources and expertise that no single country can provide. The discovery might serve as a catalyst for new forms of global governance, as humanity begins to see itself as a single species among many in a living universe. The competition that has sometimes characterized space exploration could give way to collaboration, driven by the shared recognition that understanding life is a challenge that transcends national boundaries. As you drift toward the edge of sleep, your mind filled with possibilities that stretch across cosmic scales of space and time, consider that the discovery of alien life might be closer than we imagine. Somewhere in the data, already collected by our robotic explorers, or in samples that will be returned to Earth in the coming decades, the signatures of alien biology might already be waiting to be recognized. The universe keeps its secrets not because it intends to hide them, but because it takes time for us to develop the wisdom, patience, and technological capability necessary to read the subtle language in which life writes its presence across the cosmos. Tonight, as you rest in the gentle certainty that our search continues with each passing day, remember that you are part of this cosmic conversation, a conscious participant in the universe's long process of coming to know itself. Whether we find life tomorrow or decades from now, the search itself has already transformed us, teaching us patience, humility, and wonder at the magnificent complexity of the cosmos we call home. In the quiet darkness that surrounds you, alien worlds continue their ancient rotations, and somewhere among them, life may be stirring, waiting to be discovered by instruments we've built and questions we've learned to ask. The universe is vast and patient, and it has gifts yet to give to those who watch and wait and wonder in the gentle darkness of a cosmos that may be far less lonely than we ever dared to hope.